Alright, gang, here we go. So this is Physics Unit 2, Part 3, and we're going to talk about relative motion. Alright, so let's start off here for a second. So we're looking at this guy, and so let's think about this for a second. You've got two people. One person says a car is traveling at 10 kilometers per hour, and another states that it's traveling at 90 kilometers per hour. Now you know both of them are correct. Okay, somebody tells you, I tell you, both of these are correct. How can this occur? Now the trick is you have to consider their frame of reference. So imagine this for a second. Imagine that you're traveling in a car, okay, and you're going 80 kilometers per hour, right? So you're driving along at 80 kilometers per hour, at 80, right? And then a car passes you, and this car passes you at 90 kilometers per hour, right? So from your point of view, how fast is that car going? Well, from your point of view, that car is going 10 kilometers per hour, right? That's the difference, okay? But if there was some guy, so say there was a cop out here, right? So here's our cop. So there's a cop sitting here, and he's like, here's the sirens, okay? And he's got a speed gun on you. He sees that the guy goes by at 90 kilometers per hour. So when we're talking about velocity, we have to specifically think about frames of reference, okay? So we get this thing called relative velocity. All right, relative velocity meaning it depends on where you are, depending on your point of view, in the words of Obi-Wan, right? So relative velocity. So velocity can actually differ depending on the frame of reference that you're using. All right, so in class, all right, I walked across the room and I was bouncing a ball, right? And so I walked across the room at a steady speed and I just kind of dropped the ball and then caught it and then dropped it and caught it, dropped it, caught it as I walked across the room. So if you were going to describe the ball's motion from my frame of reference, the ball's motion would be like, simply it would go down and then it would come back up, right? As I'm walking, I would just drop it and then catch it and then drop it and catch it. And it would just come straight down and come straight back up, right? Now, as you watched me walk across the room, the ball's motion did more like this, right? You'd watch me as I was walking, you'd watch the ball get dropped and it'd go down, hit the ground, and then come back up to where I'd catch it again. And then I'd drop it, and then it'd come back up, and then I'd catch it again. And I'd drop it and bounce it, come back up, and I'd catch it again. And you should notice this pattern, that it's kind of, what kind of shape does that make? Well, that makes a parabola, and we know that a parabola is usually due to projectile motion, all right? Or projectile motion is in the shape of a parabola. So we've really just got a projectile, right, that we're, dropping. It's got some sort of horizontal velocity, and then it's also got the vertical acceleration that's changing it as it goes up and down, up and down. All right. So who's correct? Is my frame of reference correct or is yours? Well, they're both right. Right? It just depends on its frame of reference. All right. So look at this frame of reference. So imagine that you're a World War II bomber pilot, right? You're going to bomb the Nazis, and so you're flying across, right? And you drop a bomb out of your airplane. Now, what you see is this bomb is just going to go, and it's got the horizontal velocity that you do. You're driving this way, or you're flying this way, and you drop this ball, and then it kind of keeps going boom, 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 until eventually it hits the ground at the bottom. Okay, now notice that from the center of the ball to the edge of the wing, that distance, whatever that distance is equal in every picture here. Okay, that this distance is exactly the same in every picture. All right, but if you were, the Nazi on the ground and you're getting ready to shoot down this bomber, okay, you would see the airplane going to the right, but then you'd also see the bomb kind of move to the right until it eventually reached its target. Now, if you looked at the shape, if you were going to draw a line through every point in this graph, what kind of shape it would make? Well, it would make a parabola, or half a parabola, right? With that, so it would make so you know that this is actually a projectile motion. All right, so these are all frames of reference. All right, it's just that simple. This is easy. This is the easiest stuff in the unit, in my opinion. All right. Now, I'm going to teach you the official way to do the math, but if you want to do it your own way, that's perfectly acceptable as long as you get the right answers. Well, without cheating. Don't cheat, all right? Okay, so anyway, so this is like the official way to write it. So we've got velocity of A in the velocity of AC. So we've got these subscripts, and these subscripts need to be read a specific way. All right, so this should be subscript. So VAC means the velocity of object A, so that's the first letter, with respect to frame of reference C. So we say the velocity of A with respect to C. That's how you'd read that, velocity of A with respect to C. All right, and this is equal to the velocity of A with respect to B and the velocity of B with respect to C. All right, and so the way this kind of works out, if you imagine, if you took these two things, if you had velocity of A with respect to B and you added it to the velocity of B with respect to C, all right, and you were going to add those together, right, combine them, then these two B's would cancel. Right? And if those two B's canceled, really what this would be turn out to be is the velocity of A with respect to C. So that's kind of how that works. All right? So that's why we write it out the way we do. All right? Now, I'm going to tell you something important here that's going to come up as soon as we do the first practice problem. All right? But for now, you just got to take my word for it. If for some reason you want to change the object and the point of view, you make your velocity negative. All right. Now imagine for a second that I've got that ball and I'm going to throw it. I'm playing basketball, right? Let's go. So there's one person here, all right, and he's got a basketball, all right, and he is going to throw it over here to this guy, right? Okay, so A and B. Okay, so person A is going to throw the ball, and if we decide that in our point of view that a ball moving away from you is positive, okay, and a ball moving towards you is negative, right now, based on this, the person A sees a positive velocity, and the person B sees a negative velocity, right? So the ball of A, this ball with respect to person A is positive, but the ball in respect to person B is negative. See how they flip-flop? And if we go the other way, if we have person A here, okay, so this is person A, and then person B is over here, okay, and this is person B, and he's going to take the ball and he's going to throw it to person A. Now person B sees the ball with a positive velocity and person A sees the ball with a negative velocity. So if we flip where the frame of reference is, that we see that we get, the reference point flips, then we get the negative because it's just the other point of view. All right, so that's going to come up here. So first practice problem here. All right, so you got a boat traveling downstream. The speed of the boat with respect to the Earth, or VBE, right? The speed of the boat with respect to the Earth is 20 kilometers per hour. The speed of the river with respect to the Earth is the speed of the river with respect to the Earth is 5 kilometers per hour. What is the speed of the boat with respect to the river? All right, I'm going to show you the easy way, and then I'm going to show you the tricky way with that math that we just did. All right, so imagine this. So imagine you've got a boat, right? So here's our boat. Don't laugh at my drawings. All right, so you got your boat, all right, and it's on a river. So here's our river, right, and we're looking down on this, okay? Now, so we know that the speed of the boat with respect to the Earth. Now, whenever you see this phrase with respect to the Earth, I have a hard time picturing that. I don't really know what that means. So what I want you to do is picture that there's just some guy standing still observing what's going on. So really, it's the speed of the Earth with respect to George that's sitting here on the side of the road. So he's sitting there and he watches the sailboat goes by, okay, and he sees that the boat's going by at 20 kilometers per hour, right? 20 kilometers per hour. Now, then he sees that the speed of the river with respect to the Earth is 5 kilometers per hour. So let's assume that he sees like a log that's going by, all right? So here's our log, okay? So here's our log, and he sees that the log's going by at 5 kilometers per hour. Now it's asking us, it says, what is the speed of the boat with respect to the river, okay? Well, really what we're asking is what's the speed of the boat with respect to the log, because the log is traveling at the same speed of the river. So what's the how fast does the log see the boat going by? Well, you can pretty easily see that it's going by, the difference is 15 kilometers per hour, okay? So that's really as hard as these get. Okay, now so that's that. So if you do it this way, that's perfectly acceptable. I'm going to show you the way the right way to do it. So if you get to college and your teacher tells you that you have to do this like mine did, then at least you'll be somewhat familiar with it in the back recesses of your mind. All right, so we're looking for the speed of the boat with respect to the river. So we're looking for velocity of the boat with respect to the river. All right. So we have to come up with this. So this guy here, the 20 kilometers per hour is VBE, all right? So VBE, Okay, so that means we need to have velocity of the earth with respect to the river, right? Because then when we combine these together, my e's will cancel. Remember how that works? And we'd end up with VBR, all right? But my problem is this guy is VRE. And I told you before, if we flip these, then we have to make that negative. All right, so the velocity of the boat with respect to the river is equal to the velocity of the boat with respect to the earth, plus the negative of the velocity of the river with respect to the earth. All right, so then that means our velocity of our boat with respect to the river is equal to VBE, which was 20 kilometers per hour. So 20 plus a negative 5. So that also gets us the 15 kilometers per hour. All right, so that's the tricky way to do it. Okay, let's do another one here. Oh, and they got the exact same answer. Thank goodness. All right. Now, so this guy, I've already got the answer posted up here because I forgot to take it off. But anyway, so we've got a plane flying northeast at an airspeed of 563 kilometers per hour, and it says airspeed is the speed of the aircraft relative to the air. All right. A 48 kilometer per hour wind is blowing to the southeast, and it wants to know what is the plane's velocity relative to the ground. All right. So let's draw what's going on. So the other way to approach problems like this is essentially a vector problem. All right, we've got a plane flying northeast at an airspeed of 563 kilometers per hour, right? So there's that guy, and he's traveling at 563, and it's traveling northeast. So that's a 45-degree angle. And it doesn't really say it's directly 45, but we're just going to assume that's right, all right? Because it makes our life easier, so we're just going to assume that's 45. And so it's got 563. And we know there's a 48 kilometer per hour wind that's blowing to the southeast. So southeast would be this direction, right? And it's 48. So there's our 48. And so this guy would also be 45 degrees. All right? And really, we want to know the plane's velocity relative to the ground. All right, so really we just need to find the resultant. Okay, it's just a vector problem. All right, so we got a 563, and we need to combine it with a 48. Now, what's the angle between these two? Well, it's a 90-degree angle. And remember, when we add vectors, the number one rule is to go tip to tail. So there's that guy there, like that. So there's 563, and there's 48. Okay, so our resultant is going to be this guy right here, right? This vector right here. Boom. So there's our resultant. All right, and we'll call that C. So if we want to find the plane's velocity, that means its velocity is a vector. So we need two things. We need the magnitude and we need the displacement. All right, so to find the magnitude, all we have to do is find the value of C. Okay, so we're just use the Pythagorean theorem. So just a shortcut here a second. So remember, a squared plus b squared equals c squared. So C would just be equal to the square root of 563 squared plus 48 squared. You plug that into your calculator and you'll get 565, right? So that is the magnitude of our resultant. But that's not the whole story. Remember, we need two things. We need the magnitude and the direction. So we got the magnitude, that's the 565, so now we need to find the direction. All right, so the direction is going to be an angle. Now, if we're going to put this on the graph, remember our 48 would slide up here, right? So this would be our 48, so our resultant would be somewhere in here. Okay, so that means this angle here is really the angle from here to here, but that doesn't help us define the angle or the direction. We need to find this angle. So if we find this angle, we need to subtract it from 45. All right, so first let's find this angle. Well, we're going to use tangent here because that incorporates our opposite and our adjacent. So you know that the tangent of theta is equal to the opposite over the adjacent. So if we want to find the value for theta, theta is going to be equal to the inverse tangent of opposite, or the arctangent of opposite over adjacent. All right. If we plug that into our calculator, make sure you set it to degrees because we're worrying about degrees here, you'll get something around 4.9 degrees. All right. Now remember that 4.9 degrees, that's this value right here. All right, but we don't want that value. We need this value, so we're going to subtract it from 45. So 45 minus our 4.9, all right, and we get 40.1 degrees, and we'll say, and then, so because it's this guy here, it's north of our east. Okay, So 40.1 north of east. So the full thing is it's a 465, so really we shouldn't have that because of sig figs. So 565 kilometers per hour at 40.1 degrees north of east. So in order to adjust, in order to maintain its heading of directly northeast, it would have to adjust, it would have to go 40.1 degrees farther this direction. Or, sorry, not 40, 4.9 degrees farther towards the north. All right? So, this is kind of what we already talked about earlier. So, two important questions. Does velocity always depend on frame of reference? Well, I hope by now that you understand that it does. Velocity always depends on the frame of reference. Okay? All right? Unless you're talking about speed of light, and then life gets more exciting. But for normal movement, non-electromagnetic radiation, velocity always depends on the frame of reference. All right. Now, ask yourself, does acceleration depend on the frame of reference? Well, what is acceleration defined by? Acceleration is the change in velocity, right? Change in velocity over change in time. Okay. So if I see, so imagine I see that a ball is falling, an apple's falling over there. It's falling, in my point of view, at 9.8 meters per second squared. That ball, as it's falling, and it's watching the ground come closer to it, it's also witnessing an acceleration of 9.81 meters per second squared. So really, does my acceleration depend on my frame of reference? No, it does not. And the acceleration is always going to be the same. So that makes life a little bit easier. So that's the end of part 3. That's chapter 3 notes in its entirety. Congratulations. All right, you're going to have a quiz coming up, so make sure you're doing practice problems. Come in for help if you need it. And I'll see you on the flip side. We'll talk about Newton's laws coming up.